Section 3.3 is rules for differentiation. So we're going to learn some shortcuts now. I want you to take just a moment and do this quick review because we're going to need these skills to do what we are about to do. So in exercises 1 through 6, write an expression as a sum of powers. In other words, create a polynomial like function. It's not going to be exactly a polynomial because negative powers are not allowed in a polynomial. So see what you can do. Take just a minute and I will come back to this. Okay, so here are our answers. In the first case, all we had to do was distribute. X squared times x to the negative 1 is x. X squared times 1 is x squared. Negative 2x to the negative 1 and negative 2. In number 2, negative 1 power means that I flip everything upside down, and then I divided x squared over x plus 1 over x and wrote those as powers. Oops. For this one, rewriting each term, 3x squared can stay the same. This is 2 times x to the negative 1, and that's 5 times x to the negative 2. This one again, dividing each term by 2x squared. This one again foiling, and this one again dividing. So splitting this to x to the negative 1 over x to the negative 3. And remember, our rule says that we subtract, so negative 1 minus a negative 3 is x squared. Negative 2 minus a negative 3 is x. Okay, so you should be able to transform into a term or a series of terms that have powers. So we're going to use that as we go through this lesson. So first of all, the derivative of a constant. And these rules are important. We're going to use them over and over and over again. If f is a function with a constant value c, then this means that the derivative of every constant function is the zero function. A constant function is a horizontal line. So let's say we have the line f of x equals 3. Okay, so that's a constant function. The derivative of f of x, if f of x is a constant, is 0. The slope of this line is 0 every place we find it. The derivative of a constant is 0. Rule number 1. Rule number 2. Oh, sorry, that's cut off. It's the power rule for positive integer powers of x. The power rule for positive integer powers of x. Okay, so if n is a positive integer, I'm sorry, I wanted to back up. Sorry, do not write that down. I want to try something first. Let's look at some of our functions that we've looked at already. All right, if I want to find the derivative of f of x equals x squared, I am going to take the limit as h approaches 0 of f of x plus h, I'm plugging it right in, minus f of x over h. This is going to give me the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared over h. My x squareds cancel. I can simplify this by dividing everything on the top by h. And when I apply my limit, I get 2x. So if f of x equals x squared, f prime of x equals 2x. We'll try another one. What if f of x is x cubed? Again, f prime of x will be the limit as h approaches 0 of x plus h cubed minus x cubed over h. That's my f of x plus h. Using foiling for my x plus h, I'm going to get x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed over h. My x cubes cancel. Dividing everything by h, I now have the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Applying my 0, I get, I don't know why I keep jumping, I get 3x squared. So f prime of x equals 3x squared. What I'm doing is I'm finding an equation for the derivative. So I can plug in any value on this function into this equation and I will get the derivative at that point. Take a look at these. F of x equals x squared. F prime of x equals 2x. F of x equals x cubed. F prime of x equals 3x squared. So let's try one more. I am not going to do this using my x plus h. I am simply going to say, following this pattern, it looks like this should be the power becomes the coefficient and the power of the derivative is 1 less. And that is our rule for powers. So the power rule for positive integers, if n is a positive integer, then the derivative d dx of x to the n equals n times x to the n minus 1. The power rule says to differentiate, multiply by n, and subtract 1 from the exponent. So there's a second rule. So now I can take any derivative for any power and just say multiply by the 7 and reduce the power by 1. The constant multiple rule. If u is a differentiable function of x and c is a constant, so c times a function, a constant in front of the function, then it's c times the derivative. So if a function is multiplied by a constant, then its derivative is multiplied by the same constant. So now if we take f of x equals 4x to the 5th, f prime of x is going to be 4 times the derivative of x to the 5th, which we now know is 5x to the 4th, or 20x to the 4th. All right, couple more rules. We're learning a lot of shortcuts. If u and v are differentiable functions of x, then their sum and differences are differentiable at every point where u and v are differentiable. So if I take the derivative of two things added together, I can take the derivative of each one separately. So if f of x is something like 3x squared minus 2x plus 1, to get f prime of x, I'm going to take the derivative of each piece. So 3x squared, I'm going to multiply that by 2. I get 6x, reduce my power by 1. Here my power is 1. Negative 2 times 1 is negative 2, x to the 0. And my constant always has a derivative of 0. So here is my function. It's the sum of several individual differentiable functions. The derivative is the sum or difference of those derivatives. Okay, we got some more. So let's see. So let's look at, here's another example. Find dy dx, differentiating this polynomial. By rule 4, we can differentiate term by term. So again, dy dx is the derivative of x to the 4th. Bring down the 4, reduce the power. The derivative of 2x squared is 2 times, bring down the power, reduce, minus sign here. The power here is 1, multiply 3/4 by 1, and x goes to the 0, and this is 0 itself, so we don't need to write it. So here is my derivative. Again, we can call this f prime of x. We can call it dy dx. We are differentiating each of the pieces individually. Notice we're using some different notation as we go along. Okay, so find any values of x such that f prime of x equals 0. In other words, values of x where there exists a horizontal tangent. So this is another type of problem we can do with derivatives. If f of x is x to the fourth minus 8x squared plus 2, and I want to know where f prime of x equals 0. First, let's find f prime of x using the rules we've just learned. 4x cubed, bring down the 2 and multiply, 16x, subtract 1 from that, and that's going to be a 0. Setting this equal to 0 to find where is the derivative 0, in other words, where is there a horizontal tangent. To solve a polynomial set equal to 0, I'm going to factor out a power. This leaves x squared minus 4. So continuing to factor to solve. And I find out that x is 0, positive 2, and negative 2. So let's take a look at what this looks like. Here's my graph of my original function, and you can see that at negative 2 it looks like I should have a horizontal tangent, at positive 2, and at 0. So these are the three places where my derivative is 0, which means where I have a horizontal tangent. We are also going to be able to use this tool to find out where the graph has minimum and maximum values. You can see that when I have a horizontal tangent, the graph is turning around. So it's a very useful tool so that I can find minimums and maximums of graphs. And they really are what we call local minimums and maximums, because this graph does continue to go up forever, but at this place that's a local maximum. These are local minimums. So another way to use this, right now we're going to use it to find our horizontal tangents. Okay, another rule, the product rule. The product of two differentiable functions u and v is differentiable, and the derivative of u times v is u times the derivative of v plus v times the derivative of u. The derivative of a product is the sum of two products. This is important. If you have two functions, it is not the derivative of the first times the derivative of the second. That's a u and that's a v. So be careful of that. We want to use this product rule. Let's take a look at it closely. So find the derivative f prime of x if f of x is the product of these two. So our rule says that if f of x is u times v, then f prime of x, and I'm going to use a little different notation, is u times v prime, the original function for u, the derivative of v, plus v times u prime. So let's take a look. Using the product rule, if u is x cubed minus 4 and v is x cubed plus 3, we're going to take the derivative of the product by keeping the original function, the derivative of the second function, plus the second function times the derivative of the first. So this is u times v prime plus v times u prime. We're going to continue by distributing and then simplifying. Whoops. So this expression is our f prime of x. So again, product rule is very important. Sorry, that wasn't the rule over there. Product rule. There are a lot of ways to write it. This is a fairly simple way. U times v prime plus v times u prime. And if we have a product rule, we probably need a quotient rule. at a point where v does not equal 0, the quotient of u over v is differentiable, and the derivative of u over v is v times the derivative of u minus u times the derivative of v over v squared. Let me write it another way. V times u prime minus u times v prime over v squared. Order is important in subtraction, so be sure to set up the numerator properly. We sometimes refer to this as low d high, so the bottom times the derivative of the top, minus high d low over the square of what's below. There's a little song that will help you remember this. Somebody remind me in class and I'll sing it to you, and we'll work on it together. So this again, our derivative rule for a quotient. So let's do an example of this one. So here's my function. So u is going to be x cubed minus 4. V is going to be x squared plus 3. Sometimes if you find the derivatives of each one separately first, it's a little easier to put your pieces together. So this is my derivative of each one following my rules. And again, remember, I think they're going to give the rule for us. So there's my u, there's my v, and I'm going to, oh, they didn't do it, so let me write it here. So remember, u over v, if I'm taking the derivative, is going to be low d high minus high d low over the square of what's below. So there's my u, or my v, that's my low, times d high, that's my u prime, minus high, that's my u, over v prime, and then the denominator squared. And again, we're going to have to do some simplifying, foiling, and writing out the numerator, doing some simplifying of the top again, and unless this top factors, we do not have to FOIL out the denominator. Leave that as a squared. Okay, we've got one more rule. So the power rule for negative integer powers is what that says. Again, it's cut off and I apologize. If n is a negative integer, we are still going to use the same power rule. It's the same as rule 2, except n is negative. Not a big deal. So find an equation for the line tangent to the curve y equals 1 over x at the point 1, 1. Well, first I need to rewrite that as a power. That's why we practiced this at the beginning. So now I can use the power rule. So this is y prime. Again, since I started with x to the negative 1, my rule says bring down the negative 1 and subtract 1 from my power. Bring the negative 1 in front, subtract 1 from 1, I get negative 2, and then I can rewrite it as a function with a positive integer power. Now I'm going to do a little bit more here. So y prime of 1, using my equation, I'm plugging 1 into this equation, gives me negative 1. That means at x equals 1, f, well, we didn't call this f, we'll just call it y prime again. The derivative at 1 is negative 1. The slope of this graph, all right, so if I take a line through 1, 1 with this slope, this should be my tangent line. So I've now created an equation for the tangent line by finding the derivative, finding the slope at 1, using that point 1, 1 to write an equation of the line, and then rewriting it in slope-intercept form. So let's show the graph. I've got a little bit more on here than I want to see. I'm going to have to erase some of this. Okay, so here's my original function. It is a rational function, and it looks like this. That's my 1 over x. Here's the equation of my tangent line at the point 1, 1. And when I draw this line, I do have a slope of -1, and it passes through the point 1, 1 on my curve. Okay, second and higher order derivatives. The derivative y prime equals dy dx is the first derivative of y with respect to x. This is some language that we use. Later on we're going to talk about taking the derivative of y with respect to a different variable. So it's kind of important to get into the habit of saying this is the derivative of y with respect to x. The first derivative could be differentiable as well. If so, we get y double prime, or dy prime over dx, or d dx of the derivative. So these are all ways to write it. We can also call it f double prime of x if we're using function notation. So this notation, this notation, this notation are all called second derivatives. If we do it again, we get third derivatives, f triple prime of x. So this is the third derivative of y with respect to x. Okay? When we get into multiple prime notation, after 3 primes it gets a little bit messy to do a whole bunch of slashes. So once we get past 3, we are going to say y fourth derivative. Watch the notation. We don't want this to look like y to the 4th power, so we put a parenthesis around it. We can also say the 4th derivative of x this way. Okay? So let's just do one that would have more than one derivative. I'm going to go ahead and use our function notation. So f of x is 2x to the 5th minus 3x cubed plus 2x plus 1. My first derivative, bring down the 5, 10x to the 4th, bring down the 3, 9x squared, and reduce our powers. Don't forget that that becomes 0. F double prime of x, bring down the 4 again, so 4 times 10, 40, reduce my power. 2 times 9, 18. Reduce my power. I lose that with a 0. F triple prime. 3 times 40 is 120. X squared minus 18. The 4th derivative of x is 240x. And this one actually would have a 5th derivative, which would just be 240, and a 6th derivative, which is 0. So you can see that we can have derivatives over and over and over. We're taking the derivative of the derivative of the derivative. We'll see what that looks like. Okay, the last few slides are a quick quiz for sections 3.1 to 3.3. I'm just going to scroll through these. If you want to try it now, I wouldn't really suggest that because we haven't done any problems on 3.2 and 3.3, but you might want to come back to it later on as you're studying for a quiz or a test. So I'm just going to scroll through. You can pause the video now and quit if you want. I'm going to keep it running so that if you want to use it later.